Let's do the stoichiometry. That will also help you for the assignment to think about that and to discuss the results. So what we have is now a generic organic matter, simplify at CH2O, which is formaldehyde if you want to have the name of the molecules, plus sulfate, 2 minus, will give you, in the simplified world, in theory, CO2 plus H2S. You're going to write the two half reaction. CH2O will give you CO2, and the second half reaction, the sulfate, will give you H2S. Okay, so the oxidation of organic matter and the reduction of sulfate. Now we're going to go through the process of balancing those equations. First thing would be to balance the main elements. Carbon is okay, sulfur is okay. So we're good with that. Now the oxygen, we need to balance oxygen by adding H2O. We have 2 oxygen on the right, 1 oxygen, we need to add 1 H2O here because we're missing 1 oxygen on the first half reaction. Second half reaction, we have 4 oxygen on the left, we need 4 water on the right side. Now we're balancing H+. We have 2 and 2 in this case, which is 4 electron. We need 4 H plus on this side. On the second half reaction, we have 2 times 4, 8 plus 2, 10 on the right side. We need 10 proton on the left side. Now we're balancing the charge by adding electron. In this case, the first half reaction, this is 0. This is plus 4, so you need plus 4 electron to balance the first half reaction. Then here we have 0 here, and here we have plus 10 minus 2. We have plus 8. So you need plus 8 electron here. Let's do it the right way here. We need 8 electron here. So we need now to have the same amount of electron on each half reaction. That means you need to multiply this one by 2. I'm going to rewrite equation 1 here. So 2CH2O plus 2H2O will give you 2 CO2 plus 8 proton plus 8 electron. Now I'm going to take my other color, let's say green, now this green here. Simplify this here, simplify here by 2, okay. Water, no more water here, 2 here. And then I will add those 2 reactions together. Writing back in white, we have 2CH2O plus sulfate, 1 mole of sulfate, plus 2 proton will give you 2 CO2, 2 mole of CO2, plus 1 mole of H2S and 2 mole of water. So we can stop here. We have a balanced equation. We're pretty happy. So if you believe that, this sulfate-releasing bacteria will, if you think about acid-base, consume 2 mole of proton. So you will remove H plus from the solution. If you're removing H plus from the solution, you increasing the pH, you're getting more alkaline, right? But if you think about this reaction here, this is a sulfate reducing activity taking place in natural environments. In natural environments, what you will have is a neutral pH. I told you life like to have a pH between minus 6.5 to 8.59. That's a neutral pH around 7, okay? So this will take place in marine environments when the average pH is around 8. So when you have an average pH around 8, we have seen that CO2, the DIC, is not present under the form of CO2, but under the form of bicarbonate. If you don't remember that, here a small reminder. I'm going to go back here. There you go. So this is for, remember, this is a pH, a marine pH zone here, okay, and this is a beer room plot, and the main form of DIC at a pH around 7 to 8, which is our pH in natural environments, in our ecosystem, it will be this, not this, okay? The same way for sulfide. Hydrogen sulfide is a gas that is a weak acid that will dissociate as a function of the pH, the same way as the carbonic acid. And in pH around 8, you mainly have the HS minus in solution, not the H2S. So now, if you simplify that, and going back to our stoichiometry here, we can write that down. Again, this is not going to be CO2 but bicarbonate, it's not going to be H2S but HS minus. And okay, now we have 2 CO2 will give you, right, plus 2 water will give you 2 HCO3 minus plus 2H plus. Same way here, we have 1 H2S that will give you 1 HS minus plus H plus. In this case, you will have creation of 3H plus 3 proton out of the changing in between the different species of sulfide and carbonate. So if you're writing that down now, taking account of this pH around 8 that you're going to form species like bicarbonate or HS minus, the final equation will be that those two H plus will be simplified and this is going to be only one H plus. So the final stoichiometry will be sulfate. It will be 2 mole of bicarbonate plus 1 mole of HS minus plus a H plus. Okay, you understand that those H plus is those 3 H plus that we created by shifting from CO2 to bicarbonate and H2S to HS minus. Those 3 H plus will be on the right side and you have 2 H plus on the left side. You simplify, you have H plus. So in this case, you see that the sulfate-reducing bacteria is decreasing the pH, getting the pH more acidic in this case, okay? And in the assignment, I want you to do the same calculation, but with different electron donor, different source of molecule of organic matter. We did that with generic organic matter. You will do that with lactate, acetate, formate, or even hydrogen. And you will see what will be the consequences on the pH. So this is a nice way to coupling redox reaction with the acid-base chemistry. In ecosystem, organisms, especially bacteria, but we are also doing that, by doing their metabolism, they're changing the environments. You see, in this case, they can increase or decrease the pH. Meaning, if you have carbonate, this metabolism here will have a chance to dissolve calcium carbonate. If you have another process that we have seen that in acid-base chapter with the photosynthesis, able to pump OH outside the cells, consuming CO2 will act on the environments to precipitate calcium carbonate. So if you are interested in the balance in the lithosphere for the limestone in terms of alteration, precipitation, this type of metabolism and how organisms such as bacterial ecosystem are interacting with this lithosphere, it is key to understand those redox equation at a very high level of detail.